Hello students, this is Sujata Madiwala. We are here at the last portion of this macromolecules chapter. Sorry for the delay of the video. Before I start, I will recommend you to have a pen and paper because this involves the derivation. So, as the quote by Benjamin Franklin, tell me I forget, teach me I may remember, involve me and I will and I learn. So whenever you involve in the subject, then only we learn in a better way. So I advise you to have a pen and paper and follow up this derivation step by step. So once you understand, you know no need to practice again and again. Mm, mm, so I advise you to follow up the video and pause the video whenever necessary and take down those formulas and the steps. So let's start this lesson. That is, there are two methods, that is determination of molecular mass of macromolecules or polymers. There are two main methods generally used to determine the molecular weight of macromolecules. One is osmotic pressure method and the other one is viscosity method. In this video I am going to teach you about this osmotic pressure method, how we are using this osmometry to determine the molecular weight of the macromolecules. Let's move ahead. That is osmotic pressure method. The osmotic pressure of a solution of a macromolecules, even at a very low concentration, are significant and can be easily measured. Hence, the measurement of a osmotic pressure macromolecule solution can be used to determine the molecular. ಈ osmotic pressure ಮೆಥಡ್ ಏನಿದೆ ಅಂತಂದರೆ, ವೆರಿ ಲೋ ಕಾನ್ಸಂಟ್ರೇಷನಲ್ಲೂ ನಮಗೆ ವೆರಿ ಸಿಗ್ನಿಫಿಕೆಂಟ್ ವ್ಯಾಲ್ಯೂ ಯು ಕ್ಯಾನ್ ಈಸಿಲಿ ಮೆಸರ್ಡ್. ಅದಕ್ಕೆ ನಾವು ಆಸ್ಮೋಟಿಕ್ ಪ್ರೆಷರ್ ಮೆಥಡನ್ನು ಯೂಸ್ ಮಾಡಿ ಮೊಲಿಕ್ಯುಲರ್ ವೇಟ್ ಆಫ್ ಅ ಪಾಲಿಮರನ್ನು ಡಿಟರ್ಮೈನ್ ಮಾಡ್ತೀವಿ. So we will move to this osmometry. Before moving to this osmometry, you must know that what you mean by osmosis, right? What you mean by osmosis, you already learnt in a PUC levels. Wait, PUC level. That is, osmosis means this flow of a solvent molecule or a water molecule from a region of a higher concentration to the region of a lower concentration through a semi-permeable membrane. That is called as an osmosis. So, and the here the osmotic pressure measurements are used for studying a macromolecules because osmotic changes are larger than the changes in the boiling point of elevation and a freezing point of depression and vapor pressure of lowering. These are four colligative property. What do you mean by colligative property? Colligative properties are the properties which depend upon the number of moles of the numbers of the solute particles. Depending upon the number of solute particles, these properties are different. Those are four properties. This you learned in a BSc first year itself: boiling point of elevation, freezing point of depression, and a vapor pressure of lowering, and as well as osmotic pressure. Then what do you mean by this osmotic pressure? This osmotic pressure means this is minimum pressure which needs to be applied to the solution to prevent the inward flow of its pure solvent across the semi-permeable membrane. That is called as an osmotic pressure. For example, this solvent are flowing through this semi-permeable membrane. This minimum amount of pressure applied on this solution to prevent the flow of this molecule, that is called as an solvent molecule, that is called as an osmotic pressure. See, for instance, for order of magnitude calculation shows that for aqueous solution containing 10 gram dm for a polymer having a molar mass 20,000 and a boiling points of elevation and freezing point of depression is 0.0025 degrees Celsius and 0.00093 degrees Celsius respectively. So this evidently these low freezing point or ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಆಫ್ ಎಲಿವೇಶನ್ನ ಯೂಸ್ ಮಾಡಿಕೊಂಡ್ರೆ ದೀಸ್ ವ್ಯಾಲ್ಯೂಸ್ ಆರ್ ಟೂ ಲೋ ಟು ಬಿ ಮೆಸರ್ಡ್. ಅದಕ್ಕೆ ನಾವು ಯಾವ ಕೊಲಿಗೇಟಿವ್ ಪ್ರಾಪರ್ಟಿನ ಯೂಸ್ ಮಾಡ್ತೀವಿ ಅಂದರೆ ಆಸ್ಮೋಟಿಕ್ ಪ್ರೆಷರ್ ಪ್ರಾಪರ್ಟಿನ ಯೂಸ್ ಮಾಡ್ತೀವಿ ಇನ್ಸ್ಟೆಡ್ ಆಫ್ ದಿಸ್ ಫ್ರೀಸಿಂಗ್ ಪಾಯಿಂಟ್ ಆಫ್ ಡಿಪ್ರೆಷನ್ ಆ್ಯಂಡ್ ಅ ಬಾಯ್ಲಿಂಗ್ ಪಾಯಿಂಟ್ ಆಫ್ ಎಲಿವೇಶನ್. ಸೊ let's start this derivation. Here pi is osmotic pressure. I already defined what you mean by osmotic pressure. Here I had represented that osmotic pressure as P. In some book they are represented as a P also. Whatever I took it from the Puri Sharma Patania, so there you can use both the symbols, no issues. So which this here the pressure of a solution in which mole fraction of the solvent is x1. Mole fraction, you already know that one. What do you mean by mole fraction? This comes in second PUC itself. Mole fraction, number of, that is equal to number of moles of the solute divided by to the total number of the solute. The ratio of the number of solute divided by total number of the total number of moles of the solute, that is called as a mole fraction we consider. And then condition for the equilibrium for a chemical potential of the solvent, we are taking here the polymer solution, that to dilute solution, and the chemical potential of the solvent on the both the side of a semi permeable membrane. So chemical potential at equilibrium only, that condition will be like this. What is the chemical potential definition? We consider RT ln gamma 1 x1 plus pi v1 bar, which is equal to 0. Call it as equation 1. This condition you need to remember. This is what the condition where the equilibrium is created, that chemical potential expression. This gamma 1 value, that is equal to activity coefficient of a solvent, and v1 bar is the partial molar volume of the solvent in the solution. Then for dilute solution, what happens for dilute solution? This x1 tending to 1. Why? Because let me explain. x1 plus x2 is equal to 1. This condition you already know that one. Whenever a number of solute are given, for example x1 is equal to what? N1 divided by N1 plus N2, this mole fraction expression, and x2 is equal to what? N2 divided by N2 is the number of moles of the solute, and the total number of moles of the solution, that is N1 plus N2. Whenever you add these two, x1 plus x2, which is equal to N1 divided by N1 plus N2 plus N2 divided by N1 plus N2. Here the denominator are same, so I take N1 plus N2. Then what remains in the numerator? N1 plus N2. So both the numerator and denominator are same. So we will get the expression as 1. So this is how this is what we get, the x1 plus x2 is equal to 1. Here the for dilute solution, x1 tending to 0. Why? Because we had to dilute solution, in the sense solutes are very low particle, but the solution is much less compared to this one. For example, this 100 number of moles are there, and this solute particle are 0.0001. If you consider 0.01 of mole it is there, we can easily tell that this is equal to nearly equal to 100 mole fraction. So x1 tending to 1, v1 bar you can consider it for a dilute solution, v1 not it is. Then coming for the, we already know the equation 1 expression. I told you to write, pause the video, take a pen and paper, you write down the expression, and if for you then you can easily follow up this video. Okay. So from the expression I already explained you, x1 plus x2 is equal to 1. Then what becomes? x1 is equal to what? That is equal to 1 minus x2. In equation 1 we are replacing this x1 by 1 minus x2. So what happens? RT ln gamma 1 minus x2 plus pi v1 bar is replaced by v1 naught is equal to 0. And for dilute solution, this activity coefficient is equal to 1. So what happens here? I interchange this pi v1, this expression to the right hand side, RHS, and this will keep it in the left hand side. Pi v1 naught is equal to minus, if you send this one to this side, right hand side, what it will be? RT ln 1 minus x2 it will be. So this is what a minus sign it is there. So how you will write? You already know that minus ln x, how you can write? Ln x to the power minus 1, or also you can write ln 1 divided by x also you can write. So I had written here RT ln 1 minus x to the power minus 1 in the next step. So then pi v naught is equal to RT. This one ln 1 minus x to the power minus 1 expression will be what it is? This will be x plus x square divided by 2 plus x cube divided by 3, and so on. Like this, I had 1 minus x2 to the power minus 1. This expansion it is, let me move this side. Okay. This will be this that I had replaced this ln 1 minus x2 raised power minus 1, that with this expansion. What is this expansion? X2 plus x2. This is a simple mathematics, you already know that one, these logarithms and all. So x2 plus x2 by square divided by 2, x 2 cube divided by 3 plus and so on. So I replaced this one by here pi v1 naught is equal to rt x2 plus x2 square divided by 2 x2 cube divided by 3 and so on. Call this as equation 2. So for call this as equation 2, and for a polymer solution concentration x2 is given by I already told you x2 is nothing but what, a mole fraction, that is n2 divided by n1 plus n2. N2 is the number of moles of the solution. How you will write the moles? Number of moles is nothing but a concentration divided by molecular weight of the substances. Concentration divided by molecular weight will give the number of moles. Here I have written in place of n1 divided by n1 plus n2, which is equal for n2, that is equal to x2, right? So x2 how you can write? C divided by m and divided by 1 divided by v1 naught, that is the molar volume of this n1 solvent, and the plus 1 c divided by m n2. So in this equation I had written this n by taking the denominator 1 divided by v1 naught plus c divided by m. So c divided by m, as I already told you, dilute solution I had took, that by c divided by m, number of moles of this n2 will be very small, so that this equation I simply write as 1 divided by v1 naught. As I already told you, solvent will be 100 plus the solute is 0.00 something, means how you can write directly, it is nearly equal to 100, right? So 1 by v1 naught is much greater than c by m, so we neglect this c by m, we directly write 1 divided by v1 naught. So what happens in this equation? C divided by m divided by 1 divided by v1 naught. So 1 divided by v1 naught ಬಂದ ತಕ್ಷಣ ಏನಾಗುತ್ತೆ, ಡಿನಾಮಿನೇಟರ್ಗೆ ಹೋದಾಗ v1 naught c divided by m we get. So v1 naught c, we call this equation as a equation 3. So by combining these two equation 2 and equation 3, what we will get? Here we will get replacing this x2 ಇದ್ದಲ್ಲಿ ಏನು ಮಾಡಿದ್ದೀವಿ, x2 value ಅಂದರೆ ಏನು, this with the help of this equation 3 we got a x2 value v1 naught c divided by m. We are putting that one into in the equation 2. What you will get? Pi v1 naught, that is equal to rt v1 naught c divided by m plus v1 naught square c square divided by 2m square plus v1 naught cube c cube divided by 3m square plus and so on. So pi v1 naught, which is equal to rt v1. See, look at this equation, whatever written in this bracket, in that one which is common here? v1 naught c by m. Here also that is there, v1 naught c by m, v1 naught c by m. So what I do here, I will take this v1 naught c the outside of the bracket, then what remains here? rt v1 naught c by m, the remaining 1 plus 1 by 2 v1 naught divided by m into c plus 1 by 3 v1 naught square by v1 naught by m whole square and c square plus so and so on. And the next step it will be v1 naught, here also v1 naught get cancel each other, and the c whatever written in the this right hand side, I will take this to left hand side. What it will be? Pi divided by c. Pi is the osmotic pressure, I already told you, which is equal to rt by m 1 plus a to c. Whatever this 1 by 2, that I replaced by a2. a2 is nothing but your 1 divided by 2 v1 naught divided by m, and the a3 is v1 naught by m whole square, 1 by 3 v1 naught by m whole square and so on like this. And this is called as an equation 4. And coming for the, we often this equation 4 also often we can written as pi by c rt by 1 by m b2 c b3 c square like this wise. What is instead of a2 we are writing b2, no changes at all. Where b1 b2 are, these are called as second third viral coefficient ಏನಂತ ಕರಿತೀವಿ, b1 b2 and b3 these ಇವನ್ನ viral coefficient ಅಂತ ಕರಿತೀವಿ. And this equation is called as an want of equation relating a osmotic pressure of a polymer solution with a molar mass of the polymer, and the quantity this 5 by c is called as an ರೆಡ್ಯೂಸ್ಡ್ ಆಸ್ಮೋಟಿಕ್ ಪ್ರೆಷರ್. ಈ 5 by c ನ ಏನಂತ ಕರಿತೀವಿ, ರೆಡ್ಯೂಸ್ಡ್ ಆಸ್ಮೋಟಿಕ್ ಪ್ರೆಷರ್ ಅಂತ ಕರಿತೀವಿ. ಆ್ಯಂಡ್ ದಿಸ್ ಇಕ್ವೇಷನ್ ಈಸ್ ಕಾಲ್ಡ್ ಆಸ್ ಆನ್ ವಾಂಟ್ ಆಫ್ಸ್ ಇಕ್ವೇಷನ್ ರಿಲೇಟಿಂಗ್ ಆಸ್ಮೋಟಿಕ್ ಪ್ರೆಷರು ಮತ್ತು ಮೊಲಿಕ್ಯುಲರ್ ವೇಟ್ ಆಫ್ ಅ ಪಾಲಿಮರ್ನ ರಿಲೇಟ್ ಮಾಡೋ ಇಕ್ವೇಷನ್ ಇದೆ. ಆ್ಯಂಡ್ ಯು ಕ್ಯಾನ್ ಬೈ ಲುಕಿಂಗ್ ಎಟ್ ದಿಸ್ C and C square you can consider C square, C cube. C ಏನಂತ ಹೇಳಿದ್ದೀವಿ, ಆಲ್ರೆಡಿ ಕಾನ್ಸಂಟ್ರೇಷನ್ ಏನಿದೆ ಲೋ ಇದೆ, 0.01 ಅಂದ್ಕೊಳ್ಳೋಣ. C ಸ್ಕ್ವೇರ್ ಅಂದರೆ 0.01 ಇಂಟು 0.01, ಸ್ಟಿಲ್ ಇಟ್ ವಿಲ್ ಬಿ ಲೋವರ್. ಆ್ಯಂಡ್ C ಕ್ಯೂಬ್ ಅಂದರೆ that will be again it will be lower. So we are neglecting these B3 B4 terms, and what we will get, what will remain after neglecting these terms, we will have pi by C is equal to RT 1 divided by M plus B2 into C. ಏನಾಗುತ್ತೆ, ಇವಿಷ್ಟನ್ನು ನೆಗ್ಲೆಕ್ಟ್ ಮಾಡಿದಾಗ, ವೈ ಬಿಕಾಸ್ ದೇ ಆರ್ ಟೂ ಲೋ ವ್ಯಾಲ್ಯೂಸ್. ಸೊ ಇಫ್ ಆಫ್ಟರ್ ನೆಗ್ಲೆಕ್ಟಿಂಗ್ ದೀಸ್ ವಿ ವಿಲ್ ಗೆಟ್ ದಟ್ ಇಕ್ವೇಷನ್ ಆಸ್ ಅ pi divided by C RT 1 divided by M plus B2 into C. So let's move here this one. Okay, so what I had written here, pi divided by C RT 1 divided by M plus B2 into C, right? So here RT by M plus B2 into C, if you consider, this is expression y is equal to mx plus C. Or else if you draw this p by, I had written p, you can write pi also, pi by C, pi or p, whatever you are using. Pi versus concentration C, this pi by C versus concentration C, the graph you plotted, you will get a straight line, and extending this one, and it will cut the y axis set, and this is called as your intercept. That is equal to, that intercept is nothing but a whatever this is what a C, and this is what mx. So RT by M is what your intercept, that is equal to RT by M. So with the help of this one RT intercept, we can easily able to find out the it is nothing but a limit C tending to 0, means here the concentration varying here in along the x-axis, and if you extend this equation, it at y-axis what happens, this concentration is equal to 0. So that's why limit has pi C tending to 0, what we will get, RT by M. So with the help of that intercept, by plotting the intercept, what you will get, RT by M, which is equal to intercept value. So easily we can, this R and T are constant, and easily we can able to get the value of the molecular weight of the polymer. So with the help of this osmotic pressure method, we can easily get the value of a molecular weight of the polymer. I will quickly go this derivation once, and this is a very important derivation. You can mark it as a danger and practice it. If you understand, watch the video one or twice, one more time again, and you will able to understand this one. So I quickly go through this equation derivation again. So very first one, you need to remember this equation 1, that is the chemical potential when then at a equilibrium condition, that is RT ln gamma 1 x1 plus pi v1 bar is equal to 0, and bar applying for a dilute condition, what happens, dilute condition gamma activity coefficient ಏನಾಗಿರುತ್ತೆ 1 ಆಗಿರುತ್ತೆ, and the value of this x1 replaced by 1 minus x2, and for rearranging the equation, and by writing the expansion of this logarithmic value and putting the value of this concentration C by M, this mole fraction ವ್ಯಾಲ್ಯೂನ ಇಲ್ಲಿ ನಾವು x2ದಲ್ಲಿ ರಿಪ್ಲೇಸ್ ಮಾಡೋದ್ರಿಂದ, then again all the mathematical steps involved, and finally we will get this pi by C is equal to RT by 1 by M plus B2C plus B3C square and B4C cube C raised to 4, and goes on. This equation is called as an Van't equation. With the help of this, by plotting the graph, we can easily able to find out the molecular weight of this macromolecules or polymers can be done. Then this is what about the osmometry. We will meet in the next class.